Okay. So, last several lectures were devoted to the Fourier transform, which we are going to use to solve some equations. But to use it, we need to know how to compute Fourier transform of some functions. And I already showed some examples. And added something in the exercises, but maybe it's better to solve some exercises now. By the way, did you try to look at them today or not? Ah, and ah. Mhm. Mhm. Ah, and so I would maybe do you have some particular questions about some of the problems? So which one? Mm-hmm. Yeah. So okay, let us uh, try to compute some integrals. And by the way, I did not ask you, but I know that some of you did not attend any complex analysis courses. And is it a general situation, or some of you attended, some of you not? So, yeah. Now, how many of you studied some complex analysis at some moment? Ah, 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 ah. Mm-hmm. Ah, because I forgot. Mm-hmm. Yes. So, uh, and what was at this lectures? So, did you compute some integrals using contraindication or not? Mm. Mm. Ah, I see. Ah, yes. Okay. Mm-hmm. 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 Ah. Mm-hmm. Mm-hmm. Ah. Mm-hmm. Mm-hmm. Ah, I see. Ah, okay. Oh, but, mm, what? Ah. Mm-hmm. 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 Ah, I see. Okay, but uh, anyway, so let us try to solve some problems. For example, there is a question like how to compute the Fourier coefficients for such a function, 1 over cosine of x minus mm, 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 oh, facts maybe 2 pi x minus cos of 2 pi a. So we need to compute the integral from 0 to 1 dx e to the minus 2 pi ix n. So when it is about integrals on a circle, Well, in principle, it can be done in different ways. In a sense, we can, well, probably let me show several different methods. Hmm? Uh, 2 pi a, cos of 2 pi a. But it doesn't matter. It's an even function. Mm, mm. So, in general, if it is integral on a circle, we can mm, switch to the variable. We can switch to the exponential variable, saying that e to the 2 pi I x equals to z. And then d x becomes 1 over 2 pi I dz over z. Uh, and this integral becomes integral over the unit circle dz over z. And here let us write this cosine and cos as z plus 1 over z minus e to the 2 pi I minus 2 pi a minus e to minus 2 pi a. Well, the advantage of such parameterization is that we know zero of the denominator because when z is e to the 2 pi I, it vanishes, and also when z is e to the minus 2 pi I, it vanishes. And it's quadratic equation, so we know all of its zeros. And so, and here we have z to minus n. So, and now we need to shrink this contours somewhere, because it looks like this. There is e to the minus 2 pi a, and there is e to the plus 2 pi a. And so, in principle, there is some point at 0 where we can have singularity when n is positive. Or alternatively, we can have singularity at infinity when n is negative. So somewhere we have infinity. So, of course, it is better to shrink this contour to the direction where we have just a single pole coming from this denominator, right? But in any case, we need to consider two different situations. So the first situation is so 1. N is less than 0. Less, less or equal than 0. In this case, this function is regular at 0, and we can shrink it to 0. And I also forgot 1 over 2 pi I. Actually, here we can just factorize this expression because we know both in zeros, and we know that it is quadratic polynomial. So it is z minus e to the minus 2 pi I minus 2 pi a z minus e to the plus 2 pi a. Here we have z to minus n. So there is just a 0 at a 0 at this point, and the residue at this point is 2 times e to the 2 pi a n divided by e to the minus 2 pi a minus e to plus 2 pi a. Right.
It's 2 pi cos 2 pi a.
Yes, thank you. So, and uh, so this computation is clear, right? But if n is greater than 0, so in principle we can do the same computation. But if you look at this formula, we see that this function is even, so that coefficient should be the same because we can change the integration variable, right? So, so for n less than 0, it is and in general, uh, uh, so let us call this Cn. So, and if we combine these formulas together, so it was for n greater than 0. If you combine these formulas together, we see the answer is this Cn equals to um, minus e to 2 pi, sorry, short value of n over cos of 2 pi a. And so, are there any questions about this? And you see, there is some remarkable property in this formula, namely that it decays exponentially with n. This asymptotic behavior of coefficients was related to differentiability of the function, and this function is infinitely differentiable. It decays faster than power. And we can also see another property. Namely, there is this exponential asymptotics for infinite n, and the question is, what is related to this coefficient in this asymptotics? So, what kind of property of this function on a circle or on a circle is related to this coefficients.
They are even.
Hmm? Uh, oh, it is. Of course, it is true. It's just a consequence of this. The fact that this function is even and real. But the question is the following. So suppose that uh, Cn Cn behaves as e to minus lambda 1 lambda plus n when n goes to plus infinity. And like e to lambda minus lambda minus absolute value of n when n goes to minus infinity. So the question is, what can we say about the original function? So the idea is the following: we have a function of x, which is a sum of Cn and originally it was defined on a circle, but in principle we can perform analytic continuation of this function. Let us substitute here x plus iy. Both are real. So then it will have another factor, minus 2 pi n y. And if n goes to plus or minus infinity, it behaves like, so we can write these two tails of expansion. So something finite plus sum of n equals some big k to plus infinity, and substitute here the asymptotics. Cn, well, e to the 2 pi I n x e to minus 2 pi. Let me actually add here some 2 pi in this asymptotics, and here just I define 2 pi and y e to Let me combine this. Actually, 2 pi n n y plus lambda plus and plus another sum with some coefficient it will be minus y. Because it was for positive part of this series, it will be for the negative part of the series, plus lambda minus. So the series is convergent when y lies between minus lambda plus and lambda minus. So right. So, and if the series is convergent, it means that it defines an analytic function in this domain. So, analytic in this domain. So, so the picture should be like this. There is x. It's kind of x and y, and so there are these points lambda minus and minus lambda plus. And the singularities of this function appear. So the first singularity will be located at this line, and this is a strip where it is analytic. So if you draw it in this exponential coordinate, then it will be conditioned that absolute value of z is less than e to the 2 pi lambda minus and greater than e to minus 2 pi lambda plus. So. So on this z coordinate, and the picture will be like this, and there will be somewhere e to the minus 2 pi lambda plus, and there will be e to the 2 pi lambda minus, and Will be this annulus. When the function is analytic. So it is the same statement about the statement about radius of convergence of the Laurent series. So Laurent series is this Fourier series on the circle is essentially Laurent series on the unit circle in the complex plane. And the statement about convergence is a statement about the radius of convergence of Laurent series. So it's the same. Mm. So, so is it? Mm? 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 Oh, so I'm saying that there is this statement about two radii of convergence of the Laurent series. People just say that there is n some of our integers cns times zn and ask so it is a Laurent series of a function in the complex plane, and it is defined on some circle, for example, or in some annals from the very beginning. But and the people ask, what are the radius of convergence of this series? And one answer is that we should look at the asymptotics of these coefficients and this and and so how to say this also, the statement is that this radius of convergence can follow from the asymptotics of the coefficients, but we don't need to know this asymptotics. We can just look at the complex plane and find the first singularity inside and the first singularity outside, and they will limit the domain of convergence of this series. Because uh, if so we are studying the asymptotics of expression like this. When n goes to plus infinity, so it should go to 0. When n goes to plus infinity or n goes to minus infinity, it gives some condition, or n goes to minus infinity. It also gives some condition. So, hmm?
So
Hmm?
what we actually did was show that the same is true for a Fourier expansion. Yeah, like
Yeah.
I can look at the pole of convergence by looking at the expansion of the coefficients,
Hmm?
when the asymptotic of the coefficients.
Yes. Well, here the Laurent series and the Fourier series, it's really the same, just about the change of variable. But, so, yes, so what else about this? And if we have some polynomial decaying of this coefficients, it means that we actually moved some of the singularities in the complex plane to the to this unit circle. Because otherwise, if it decays exponentially, it means on this. Mm. And okay, and let us also ask the following question. Maybe better to do it for the case of well, we can do it. Or maybe let's better do it for the case of the complex plane. So let us first compute the integral of this kind. Uh, Actually, the integral which represents delta function. It's actually the inverse Fourier transform for this delta-like sequence. Dx over phi epsilon over epsilon squared plus x squared. So this e to the minus 2 pi I minus ix. So it is actually very similar to this one, and here we can again say that there are two poles. Probably we computed it already, or not. Or
Should that be p, like e to the minus I?
yes, thank you. So like this, and now we computed for real p, so that it is convergent. And now it is important if p is positive or negative, like it was important in this situation. So when p is positive, asymptotics of this exponential at plus infinity is positive, and for minus infinity it's fine, it is negative, so we can close the contour in this direction. And when p is negative, then we should close it in the opposite direction. Like this. And here it will be a single residue. So and I missed this epsilon. So p greater than 0, it will be the integral in the clockwise direction around point minus I epsilon. It's plus I epsilon. So it will be minus 1 because it's a clockwise direction. It will be 2 pi I over pi, because it is here, times epsilon, 1 over minus I epsilon minus I epsilon. So in total, it is, and I forgot the exponential itself. It will be minus pi minus p epsilon. So in total, it is just e to minus p epsilon. So when p is less than 0, there will be no null factor. There will be 2 pi I over pi as before times epsilon times e to plus p epsilon divided by I epsilon plus I epsilon. So it will be e to the, sorry, p epsilon. So in total, this gives e to the minus epsilon absolute value of p. And this is what we started with. So it's the Fourier. So this expression was Fourier transform of this. So everything is consistent. Right. And we also see that again, if we send epsilon to 0, then Fourier transform of a delta function is 1. Fourier transform of 1 is delta function. But this was actually too complicated problem, because we had two poles in this function. Now let us study what happens if we take just a single pole. Maybe better to write B. Who can tell what is the Fourier transform of such function? What is the value of this integral? Maybe let us put here plus I epsilon again.
E minus x times epsilon times I. Or a constant. I don't remember the constant.
Oh, so let me think. But you are saying this. No, it's definitely not with this, not with this sign. But if, for example, the question number 0, for which x it is, well, is it the same expression for positive and negative x or not?
Yes, that should be, yeah.
Mm. But let us remember this argument. If we need to close the contour, we need to choose it according to the behavior of this exponential. If this exponential goes to a...
Yeah, maybe for x for x bigger than 0, the exponential, the pole is not in the contour. Yeah, so I think it's 0. Yeah, for x less than 0, it should be what I said before. Or
but a little bit more carefully. This P is P equals to minus I epsilon. You substitute minus I epsilon times I, so it will be plus x.
yeah.
E to plus epsilon x. Times actually, so we go in the clockwise direction and and also multiply by 2 pi I, so it will be coefficient minus I in front of everything. Okay, and so are there any questions about this? So we can write it as minus I e to the epsilon x times it's called Heaviside theta, and it is of minus x. Heaviside theta is a function which equals to 1 for x x greater than 0. It is 1 for x less than 0. It is 0, and for x equals 0, we can define it whatever we like. We can, for example, say that it is 1/2 to make to make it symmetric, but it doesn't matter. We can say that it is 1 or 0. And you see this property, which we already proved, that if Fourier coefficients or Fourier image behaves like 1 over n or 1 over p in this case at infinity, it means that our function is discontinuous. So we have this jump here. I showed this example to show the general phenomenon. The general phenomenon is the following: if a function is analytic in a half plane, then its Fourier image is 0 on a half line. precisely because of this argument. Because if it is analytic, it doesn't have poles and it behaves in some controllable way at infinity, so it doesn't go to infinity. It doesn't have poles in there. You can just close the contour in appropriate direction for half of values of x and see that the integral actually vanishes. And if we want to see it in the opposite direction, so here we showed that if it is analytic in a half plane, that it will be that then image is zero on a half line. But how to check the opposite direction? It's also simple because let us say that f tilde of p or so let us write that f of x. Mm, so mm, okay, let me write it in some formal way. Mm, kind of. So for this direction, it is this argument with contour that we are computing integral of I px f of p dp, and suppose that it is analytic in the upper half plane. So all poles are here. Then we can close this contour for positive x. There's a picture for x greater than 0. So the integral is 0 for x greater than 0.
So when we talk about a plane, we mean the open half plane. So if I pole on the axis, it's not okay because I cannot move this anymore.
If pose on the axis, we need to define this integral somehow. And better to say that in this situation we should well, we should really say what we mean by this. Because pole on the axis can mean that it is either a little bit above the axis or a little bit below the axis. Or one half of the two situations. So it should be defined. Mm, mm. So, and I will discuss it later. Because, for example, you see this problem, and you see what happens when we cross the axis. So when epsilon is positive, then it is this function, but when it is slightly negative, it will be this function. Maybe with the opposite, yeah, with the opposite sign. And the intermediate situation, it is something in between. So if you take one half of pole shifted a little bit up and a little bit down, it will be the generalized function, which is called the principal value. And mm, mm, it should be understand precisely in this way. So if it is principal value, then you can count that it is something both above and below the the real line. So Okay, and let us. Hmm, so, are there any questions? And now about the opposite direction. So if some function is zero or on the negative on the positive half line, so f of f tilde of sorry, I should have put f tilde of p here for the Fourier image. So f of x is 0 for x greater than 0, then the integral f of f tilde of p will be the integral from minus infinity to 0 d dx e to the minus I px f of x, and if you substitute p equals to something like a plus ib, then and probably also let us flip the domain of integration. So we can write it as integral from 0 to infinity dx e to minus bx plus I ax f of x. And you see that if you send b to plus infinity, this integral becomes convergent even better than it was on the real line. So it is convergent for any value of b. So if convergent initially, uh, so and if this so if it is convergent, then it defines some analytic function. So this f tilde of p analytic. So are there any questions about this? And yeah, concerning the situation when we have a pose on the real line. Mm, so mm, so let us look at the function p plus 1 over p plus I epsilon. Uh, it can be written as so we can write imaginary, real and imaginary part of it separately. So uh, how to do this? So let us write like p plus I epsilon 1/2 of plus 1 over p plus I epsilon minus I epsilon plus 1/2. So this will be p over p squared plus epsilon squared, and this will be minus I. Uh, Let me write it as minus I pi mm, epsilon over pi uh, mm, p squared plus epsilon squared. So we already saw this expression, and it was a sequence that converges to delta function, in the sense to a function that has integral 1 and is 0 in all points except 1. And here it is some different object. So it is a function that is 1 over p in all points except 0, and it behaves like p around 0. So, and let us introduce the following name: p epsilon of 1 over x, and that one is minus I pi delta epsilon of x. And let me actually define what are generalized functions. So, uh, generalized functions are elements of space of linear functionals on some infinitely differentiable functions with smooth support. But let me maybe tell the definition later. But for now, just try to study the properties of this function. So it is not very well defined, like in the sense of pointwise convergence or something like this. But we see that it appears as a result of the Fourier transformation, for example. Or in other words, we can take Fourier transformation of such function. In a sense, we could, in principle, take this first term, send epsilon to 0, compute the Fourier transformation, and it will give us some function. Namely, it will be a sine function, right? So. So if you compute hmm, if you compute the integral from minus infinity to plus infinity of dp over 2 pi e to the I. Mm, mm. Oh, sorry, I wrote x and it was p. Sorry. So what changes in this case? So uh, who can tell what will be the answer here?
So in when x is less than 0, it should be the same as before because x is the same pole.
Yeah, but it was 1/2 because half of this pole is below the real line, half is above.
Yeah.
So it is minus I over 2 e to the epsilon x, and in that case,
It should be plus 1 over 2
mhm,
e to the minus epsilon x.
mhm, yes, thanks. So we can write that it is uh, I over 2 uh, sine function of x times e to minus epsilon absolute value of x. So it suggests that we can take a limit of this function when epsilon is 0, and we will still have the definition of integral of some function with this function. But let us see what it is. So if we compute integral of dp of some f of p times this p epsilon of 1 over p. Mm. So this integral will be what? It will be f of p p over p squared plus epsilon squared. And we can say that this integral this integral can be separated into two parts. One is a very small integral around 0. Hmm. Let us say that it is an integral from minus infinity to maybe uh, what to square root of epsilon. So let me think if it is enough. Maybe yes. Hmm?
Can you explain explicitly what is p of epsilon?
It's just a single character. So it's people use different notations for this function, and I don't remember all of them. Sometimes they write like this. Sometimes they write like VP, like principal value. Mm. And I just modified this notation in this way.
Yeah, so it's a function that
So,
how it behaves.
oh, in this case, it is just this particular function, p over p squared plus epsilon squared. So there is such integral plus a integral from uh, minus square root of epsilon to plus square root of epsilon. Uh, mm, mm, mm. Actually, probably we can do some scaling right at the blackboard. P over p squared plus epsilon squared. Mm. So, mm, so let us say that for this integral, p equals to square root of epsilon times y. Mm. It will be integral from minus 1 to 1. Here it will be dy. Mm. Oh, no, sir. Maybe I've chosen this integration domain in the wrong way. Mm. Oh, it is fine. If a scale variable in this way, then we have such a integral. Then we still need to expand it in epsilon, and at zeroth order of epsilon, it is just zero, and because this oh sorry, y squared plus epsilon. Mm. everything else cancelled. So and at zeroth order it is 0, and because this function is odd, so we need to expand into the first order. So it will be integral from -1 to 1 dy y squared f prime of square root of epsilon y over y squared plus epsilon times square root of epsilon plus higher corrections in principle. But the point is that this integral goes to 0 in this limit. Because we expanded the Taylor series, and the zero term here is constant, and this function is odd, so it vanishes.
But in the second integral, less a factor
Hmm?
no, perché poi va semplificata con l'epsilon per poi dare ma una, c'è il quadrato. Uno, due esce. No, allora poi sotto.
The question is what is the value of this integral y squared over epsilon squared plus epsilon, right? Sorry, I didn't think about this. But this expression will be less than 1 because this is greater than this. So, so it's really like integral of f prime. So this goes to 0, and epsilon goes to 0. And so, are there any questions? Oh, yes, fine. And about this integral, we can say that this is up to order of some no. So I want to say that if we start from a square root of epsilon and end at minus a square root of epsilon, then p squared will be much bigger than epsilon squared. So in this case, so this integral equals to integral of minus epsilon to minus square root of epsilon plus integral from square root of epsilon to infinity dp over p f of p plus probably again of square root of epsilon because we need to estimate it precisely if it is interesting for someone. But I think this integral behaves this way. I think this one should also behave in a similar way. But the main point is that this function in this domain just converges to function 1 over p. So, so the answer is that this integral in the limit when epsilon goes to 0 is integral uh, from minus infinity to some minus, well, let us call it epsilon prime, plus the integral from epsilon prime to plus infinity, dp over p, f of p, limit when epsilon prime goes to 0. And it is a well-defined object because it does not depend on epsilon and epsilon prime, and since this integral actually exists. And it's a way to define integral dp over p so that it is well-defined and convergent. And this function, which can be integrated with some continuous and differentiable functions, is called principal value of 1 over p. So and there is this principal value of 1 over p is by definition limit when p goes to 0 p over p squared plus epsilon squared. By the way, so we can take the limit epsilon goes to 0 in this Fourier transform and see that Fourier transform of this generalized function is a sine function of x. And the Fourier transform of the delta function is just 1. So the difference is that for one function it is 1 at plus infinity, 1 for positive x minus 1 for negative x, and for the other function it is 1 for all possible values. So it shows that well, it's another illustration to this formula that this functions appear in such combination. So if you try to compute the Fourier transform of this, which is originally 1 over p plus I epsilon, we will see that it vanishes for positive axis. Like we can do it even after this limit, after we take a limit epsilon goes to 0.
But for the Fourier transform, the limit, don't you have the I over 2 factor?
Yes, we have, but but this function is not is also not a delta function. It is minus I pi times delta function. So everything is of course up to this I factors. Hmm?
F is constant.
No, f is arbitrary function which so for this function it will be sufficient that it is continuous at 0. Let me think. Yes, it's enough that it is continuous because, for example, if we don't know about all this, we don't know how we obtained this integral, and we want to prove that this limit exists. What should we do? We should compare this expression for different values of epsilon prime. So let us define this I epsilon, which is an integral from minus infinity to epsilon plus integral from minus epsilon from epsilon to plus infinity dp over p f of p. And we want to compare I of epsilon minus I of epsilon prime. So it will be the integral from from minus let me think. Oh, maybe from minus epsilon prime to minus epsilon plus integral from epsilon to epsilon prime, right? dp over p f of p. So we can rewrite it as integral from epsilon to epsilon prime dp over p f of p minus f of minus p. So this integral does not have a singularity at p. Well, no, how to say it? There are two possible options. One is that f of p is discontinuous. So f of so a limit of p greater than 0, well, p to 0 plus of f of p is f plus limit from the opposite side f of p is f minus. And then it's integral from epsilon to epsilon prime it will behave like dp over p f plus minus f minus. And it diverges when epsilon goes to 0. It will behave like a minus a log of epsilon f plus minus f minus. And but if f plus equals to epsilon, so it was the first option. The second option is that f is continuous. So then this integral has a limit when epsilon goes to 0, and also so we can say that this integral goes to integral from 0 to epsilon prime dp over p f of p minus f of minus p. Actually, why did I take on the difference? On principle, we can say that, well, if you want to prove something rigorously, then we can say that here this, let us say that one of this epsilon is epsilon, another is 2 epsilon, and then so epsilon prime equals to 2 epsilon. And then it will be minus, it will be log of 2 times this. So expression for epsilon and 2 epsilon is different. But when just write like this. So in this case, it will be f, it will be p f to f prime of p. So it will be approximately 2 epsilon times f prime of what of epsilon plus all of epsilon squared. So no, well, better try just f prime of 0. Or maybe we can even consider a function that aside that its derivative is not continuous, and it's also not a problem. So we can write here f prime of p plus f prime of minus p, and it will be so. Maybe let me change epsilon prime to 2. Well, it is fine. Maybe just leave epsilon prime.
During this equation, we are assuming f differentiable, but not just the piece.
No, the question is what happens if f is not continuous? The limit doesn't exist. Then what if it is continuous, but its first derivative has discontinuity at 0? Yeah. And the answer is that it's also not a problem, because this. So we see that I epsilon minus I epsilon prime is less or equal than some constant times epsilon minus epsilon prime. this converges. It means that I epsilon has a limit when epsilon goes to 0. So and the integral is defined.
Just curiosity, there is a way for when f is continuous to establish an upper bound for the difference, like yeah, maybe I cannot get the two complete the same. I have some prime, but maybe there are two succession to sequence of numbers that converge to 0, such that the difference is almost 0.
No. You see that. So the idea is the following: we cannot compute the integral to 0 through 0 because this expression it doesn't. This integral just diverges logarithmically. We have dx over x, and we will get infinity. The idea is that we can define this integral symmetrically. It's a very natural definition, of course. So we cut it in a symmetric way. If we and then if function is continuous, then this divergence on the left side and on the right side cancel each other, and we can define it in such a way. And if it was not true, they just don't cancel. It is precisely what I computed here. So yeah. So and this integral diverges as it is expected.
And I can maybe solve the problem for this continuous function considering a double limit there in the definition. So epsilon prime and 7 equals to 0.
But you will need to send them in some strange way, in a sense. They will go to 0 with different powers of epsilon, because for example, if values of this function are at least both positive on the left and on the right, then you can send it to 0 as different powers of epsilon. But if one is positive and another is negative, there is just no way to define it, because the integral will be positive on both sides and both integrals diverge. So, but no one is doing this, because like it's an integral which will be specific to this function.
Yeah.
So not universal. Okay. So.
In the case number 2 in which f is continuous,
Mm-hmm.
like in the second,
Mm-hmm.
in the second step, where did the p as the denominator go?
I've just expanded this function as a Taylor series. I said that f of p is f of 0. Sorry. I should have written. No, sorry. I should have written here just f of 0 plus, and here f of 0 minus. Well, I could say that it's a L'Hopital rule, but better to say that we just expand it as f prime of 0 times p plus and so on, and this so f of 0 plus 0 minus plus f prime of 0 minus p plus and so on minus. So, so, any questions about what is going on?
We would like to ask you something about the lesson, not this specific lesson, the lesson in general. Is it possible for you to maybe write what you're doing before doing it? Like now I'm giving a definition, doing an example or something like that, or something like that, or to say out loud what you're doing, like passages, like I'm using Taylor. Explicitly, is it possible?
Yes, I can.
It would be very helpful because
Yes, but
we have difficulty to understand
but
what we are doing.
but you can just stop me if something is unclear, and so it's better if you do it immediately if you don't understand what's going on. So.
We'll try it. It's just not to maybe interrupt the lesson too much and lose the flow.
No, but well, the final goal is to explain what's going on, and if it is unclear, then it should be said in some different ways. So just ask until it becomes clear. So. Yeah, but I will try to say all this more explicitly. Okay. But are there any particular questions about what was going on here, or it is finally clear? Not. Huh. Hmm? The second one, yes, like. Hmm? Because so the integral is this minus one to one dy f of y of square root of epsilon y y over y squared plus epsilon. So this is clear, right? That it is obtained after the scaling from this integral, right? So, so it is p and p squared. So these coefficients are the same, and epsilon is cancelled. And now if this f has Taylor expansion at 0, and we suppose that it is good enough, because it will be too much troubles if we have f with some discontinuities of derivatives, and we also have this epsilon sequence. So let us just say that it has Taylor series to minus 1 to 1 dy over dy y over y squared plus epsilon, and this is f of 0 plus square root of epsilon y, f prime of 0 plus 1/2 epsilon y squared f primes of 0 plus and so on. Now the first integral. It is 0 because this function is odd. So this first integral goes to 0. And, a second integral equals to something. Third integral also goes to 0. So the next integral will also be 0.
Is discontinuous in zero.
Then we saw that this integral just is just not defined. So it should.
So in this case, f is continuous in zero.
Yes, yes. Because we checked that we are checking that this generalized function is well defined when we choose another regularization of 1 over x. So here it is this kind of more continuous regularization, and in this case we just why did so in this case, we just say that it is 0. We cut some vicinity of 0 and say that it vanishes identically. So, and I'm saying that the two regularizations are the same in a case when f is continuous, because for discontinuous f, it does not exist at all. So there is no reason to prove that something is equivalent.
L'abbiamo visto alla fine, quindi cioè, alla fine abbiamo preso il caso che
Yes.
Yeah, in the derivation we used that f is a continuous dependent function. So
Yes.
f is obviously at least differential
Uh,
or differential equal to times in zero.
But here I just did not want to, well, probably I just can neglect these terms and say that it is plus all of plus all of plus all of epsilon, and write it here, so that I don't say explicitly that the other terms of this expansion exist.
But the preference here is still the derivative in zero.
Yes, but if we want to do this for this function with jump in the first derivative, we should divide this integral into two. There are no divergences, so it's doable, and we will have the average of two derivatives for positive and negative x. But, so. Okay. But it is just some remark that we can extend it even for such functions. In reality, I don't know if there are problems where it is important, precisely the possibility to extend to this class. But is it fine now? Yes. Okay. So uh, uh, now, so, so there are a few minutes. So so-called generalized functions, which are defined as linear functionals on the space of some good functions. And by good, people usually mean that they are infinitely differentiable on R um, with compact support. So there are functions of this kind, like so there should be zero of at plus or minus infinity. Hmm? Hmm? Linear functionals on the space of this of these functions, like C infinity on R, on this, of some good functions. Mm, 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 no. I'm saying it this way because people develop this general theory for such functions, but in reality they are applied to not necessarily to so good functions. For example, they can have only a few derivatives. So the only question is if the object we get makes sense. So, mm, but uh, and the linear functionals are so linear functions or linear functions. It's probably just the same, but one is for the infinite dimensional space. So if uh, uh, phi uh, is an C infinity of R, and f is some generalized function. Then uh, we can compute a pairing of these functions. It's some number, or maybe a real complex number, maybe better. Not that complex. It's complex, but it's not important. Uh, and, so usual functions are also in this space because we can write that this pairing between f and phi is just the integral from minus infinity to plus infinity, uh, plus infinity dx f of x phi of x. So it's a kind of a scalar product, but spaces in which these functions lie are different. So one is C infinity with compact support, or just C infinity, and another is a generalized function. And the main property of generalized functions is that they don't exist outside of this context. They can only be applied to this C-infinity functions. Mm. In a sense, we cannot ask in general situation what is the value of generalized function at some point, or what is the product of two generalized functions. Uh, because, for example, we can ask what is the product of delta function times delta function, and it is some object which does not exist, and in principle it appears in physics and quite often, and it means that something should be defined that our definitions were not complete. So, but if we do like this, if we say that these functions can only act on the space of normal functions, then everything is fine. And we saw examples of such generalized functions. For example, delta function, this principal value of 1 over x function. So,
How can it possible that the integral of f times phi? I don't know how to explain, but phi is a real function.
yes. No, not necessarily. So, well, everything. Hmm? Oh,
But phi is a linear function.
a linear in the sense that f1 plus f2, 1 plus f2, some lambda f1 plus mu f2 phi equals to lambda f1 phi plus mu f2 phi. Right, linear in this sense. So was that a question on not?
Allora c'è phi di x non funziona in grandi valori.
One second, because we have problem with English,
Ah.
I don't understand first
Ah.
yeah, and then say clearly.
So,
Yeah. È tipo una funzione tipo il valore principale abbiamo detto prima. È la stessa cosa, per il prodotto scalare col valore principale ottieni quelli integrali là. Ma il fatto è che quello di numero di Dio è che f vive, cioè f è un funzionale, cioè quindi prende funzioni e le sue funzioni. No, f è una funzionale. Generalized function is consequently a natural function.
Come non spieghiamo questo?
Yeah, f is a function in the definition. Phi is a test function and f is a linear function.
yes, on the space of such functions. So
Yeah, but how do you define this scalar product? I mean,
oh, it's a pairing, not
yeah, no,
yeah, okay.
f should be a linear function on the space of functions.
No, no, let me say like this. So if it is some arbitrary generalized function, then there is no such formula in principle. If you think only about the actual functions. So if f is the actual function. So if f is the actual function, we can define this pairing is defined as this integral. So, yeah. So
Ok, quindi cioè, in generale quella che fa ancora esplicita, che è quella che puoi integrare, c'è anche una funzione. Generale sotto la specie di prodotto scalare come integrale. Ok, sì, ora funziona.
Perché Chess posso rappresentare le funzioni come prodotto scalare. Quindi già funzionale dove agire e agisce come prodotto scalare per altre funzioni.
Che sono quelli che poi
Esatto.
ok. Meglio sul
yeah. Yeah. So so if f is the actual function, define it this way. But if it is, for example, delta function, then a pairing between delta and phi should be defined like just defined as phi of 0. And if we can prove that it does not exist for the actual functions, that it is not possible. And we can also define that a pairing between this principal value of 1 over x and phi is a limit epsilon to 0, this integral. So we can define it, and then if we want to think about them as about usual functions, we can say that okay, there is this generalized function which is not the actual function, but there is also a sequence of usual functions. Namely, there is this delta epsilon, a sequence of functions, and we checked. So, for example, this computation checked that for this p of 1 over x, there was previously the computation for delta of x. So, what we checked that a limit this of this pairing when epsilon goes to 0 uh, is equal to a phi of 0. And in this case, we proved a limit when epsilon goes to 0. Epsilon goes to 0. So for any phi in this space, and here also for any phi in this space. So it equals to this. So we can say that it equals to a pairing between p of 1 over epsilon phi. So if this holds, in the sense that if this converges for any function phi, then we say that maybe in both sides that it's by definition that this sequence of delta epsilons converges in the sense of generalized functions. Delta epsilon of x converges to delta of x. And Oh, sorry, 1/x. So it's called a convergence in a weak sense, and this term is used when something converges for any test function in this class.
So the space of generalized function is the completion of the space of linear continuous function. Yeah, for every generalized function, I can find a sequence of linear continuous function that converges to it.
Let me think. Uh, Definitely any generalized function which people use anywhere can be described in this way, but in general, um, in general, um, I think that the answer should be yes, but I don't know for sure. Yeah, so. Yes, so mm, do you have any questions or so? So, yes. So, I think we should stop now because I'm out of time. But if you want to ask something, I can answer. Uh, Maybe tell something more. Ah. Mm-hmm.
We'll let you know next
Mm.
time
Yeah.
we're
Mm.
going now the slide of our previous lesson.
Mm-hmm. Okay. Yes. Welcome. Thanks for attention. Mhm.
Try to solve to put in
Mhm.
Pythagorean form.
Sorry, let me turn off the recording.